Okay, problem 3 here is a physics slash mechanics slash biomechanics problem. We have an athlete who's jumping, and based on the forces that they produce against the ground while they're jumping, we're going to calculate the peak height that they reach with their center of mass during the jump. Don't worry too much if you don't really understand the mechanics that are going on here. Like if you're working through this and you're kind of just going through the motions and you feel like, oh, I got the same answer that Dr. Miller got, but I don't really understand why it was solved this way. Don't worry about that if you feel that way. That's to be expected at this point. This involves some biomechanics that we haven't covered in class yet, that we haven't taught you yet. And this problem at this stage is similar to the previous problems, just to get you some experience in doing the kind of things in Microsoft Excel that we're going to be asking you to do throughout the class here, and giving you some practice in taking equations from physics and implementing them in practice in Excel and solving them in Excel and using them to derive values of biomechanical quantities. So that's the point of this exercise here, and all these exercises really, just gaining some experience and familiarity with using Excel for biomechanics applications. Don't worry at this point if you don't really understand the biomechanics that well. We'll cover it in some greater detail and give you some more practice with understanding that and checking your understanding for those sort of things later on in class before we have exams on these types of things. Okay, this is a jumping problem, and like I said, I'm a visual person, so I like to see examples of these things visually when we can. So I'll pull up my photo booth here and kind of demonstrate this. So my little Chewbacca doll here is going to be my jumper, and this is a case where he's standing still, straight upright, and then he's going to press his feet into the ground and generate a force against the ground with his feet that's going to propel him upwards against gravity. Okay? And I'm simplifying things here a little bit, but the greater the force that he generates against the ground, and the greater the extent that it exceeds gravity, exceeds his body weight, the faster he's going to take off from the ground, and the greater the height he's going to get to before gravity wins out and takes that velocity away and starts pulling him back down towards the ground. Okay? So there's kind of two stages to solving a problem like this. There's the ground contact part, when there's two forces acting on him. There's gravity pulling him down into the ground, but there's also his feet generating a reaction force pressing him upwards against gravity. Okay, and that's going on as long as his feet are on the ground and contacting it and generating that contact force against the ground from Newton's laws. Then, after he leaves the ground, so from the instant his feet first leave the ground and up until he's airborne and going back down to the ground, then there's only one force acting on him. Then there's just gravity. Okay? So there's one set of mechanics at play when he's on the ground. We'll use one relationship there to figure out how fast he's moving vertically when he leaves the ground, or what his takeoff velocity is. And then once he leaves the ground and there's just gravity acting on him, then he's a projectile, and we can use a different set of mechanics to figure out how high does he get before gravity wins out and starts pulling him back down. Okay? So we'll solve this problem in two stages here, dealing with that first stage when he's generating a contact force under his feet against the ground, and that's when hint 1 is telling you about here. And then once we've figured out from that ground contact phase how fast he's moving vertically when he leaves the ground, then that's where hint 2 comes in here. It says, okay, once he's left the ground, then use these mechanics here to figure out how high he gets before he turns back around and starts falling back to the ground. Okay? And again, don't worry too much if you don't understand, like, well, why do we do it this way? And why do we do it that way? How would I know that in another problem like this if I'm not specifically told which equations to use? You won't know that at this stage. That knowledge will come a little bit later in class. At this stage, we're just getting some practice in using these types of equations and solving them in Excel. Okay, let's see another visual example of this to get us started. This is a case of something that we will use later on in class called a free body diagram, where basically we draw a picture of what we're working with, in this case a jumper, and then we're going to draw all the forces acting on that jumper's body to figure out their motion. So here's my jumper, and jumper's going to have two forces acting on him when he's touching the ground. He's got gravity, which is acting on his center of mass here, m times g. And then he's got a contact force under his feet here, acting upward. And I'm going to call that contact force FV, V for vertical. Okay. And my net force in the vertical direction, if you think about what's on average during this time when he's jumping and pressing his feet against the ground, what's the average net force he's generating in the vertical direction, that would be the sum of those two forces. Okay. So that would be FV plus mg. And if you're confused on this sign here, if you're thinking, well, your gravity, your mass times gravity, your weight there is pointing downward, so shouldn't that be a negative sign there? It will become a negative sign once we plug in a negative value for gravity here. If I assigned a value of g of negative 9.81, which I think I did, yeah, in the problem there, then my weight here, my force due to gravity, will become a negative force, a force opposing my upward vertical ground reaction force there when I plug in a negative value for gravity there. If I had given a positive value for gravity there, then you would have wanted to account for this being in the negative direction by sticking a negative sign on front there, like that. So whether it's positive or whether it's negative kind of depends on when do you want to account for this. Do you want to account for it in the drawing here by saying, okay, this is a negative force and I'm going to want to plug in a positive value for gravity or else it's going to cancel that out? Or do you want to just sum everything, just add them all up regardless of whether it points upward or downwards, and then account for the direction later when you plug in the values of gravity and things like that. So you'll get the same result either way. It just depends on, are you accounting for it in the symbolic form of the equation, or are you accounting for it in the values of the symbols that you'll plug in later? So here we're accounting for it by saying we're going to plug in a negative value for gravity there, and this is going to become a negative overall force. Okay, hint number 1 tells us this is an impulse momentum problem. And our impulse momentum relationship from earlier in this section of the lab handbook said that I apply some average force on some mass for some amount of time or some span of time, delta t. And that's my impulse, my average force times the amount of time that force is applied for. And that equals, so that impulse equals my change in momentum, which if my mass is constant, which while I'm over the time span of jumping here, my body's mass is staying more or less constant, then that impulse equals the mass times the change in velocity that occurs during that time. Okay. So this change in velocity, you can also think of that as mass times the velocity that I start at, we'll call that the velocity that I end up at, v1, minus the velocity that I start at, v0. Okay. So what is v1 and what is v0? It depends on my movement that I've defined here. It depends on what's happening physically during this delta t, this span in time that I'm dealing with. So we're told we start at a case when we're standing still, like standing straight up and down vertically on the ground, meaning my initial velocity here, my velocity when I'm standing still, is going to be 0. Okay. Then at the end of delta t there, I've left the ground, or my feet have first ceased having contact with the ground, and in that case my velocity v1 here is not going to be 0, it's going to be my takeoff velocity, the vertical velocity of my body's center of mass as I immediately left the ground there. Okay. So my impulse momentum relationship here reduces to F delta t equals my mass times my takeoff velocity of my jumper. Okay. So if I want to solve for my takeoff velocity, I find my net force in the vertical direction and multiply it by the amount of time that force is acting on me. I divide that impulse by my body mass, and I get my takeoff velocity. So let's go to my spreadsheet and actually do these things. And I tried to lay this out for you in a helpful way. You've got everything that you're given, everything that you know about the problem here, and then you can calculate all the things you need here step by step to arrive at the peak height of the jump here, which is our goal. So first is my net vertical force. That's my ground reaction force plus my weight. So that's going to be ground reaction force, the 950 newtons, plus my mass, times my gravity. Should be about 214 newtons. I then take that average net vertical force times the contact time, or the amount of time my feet are in contact with the ground producing that net force. That was that 0.9 seconds. That gets me that impulse. So that's this left-hand side of my equation here, F delta t. And then I divide that impulse by my mass to be left with my takeoff velocity all by itself on the right-hand side there. So take my impulse, divide it by my mass, and I get my takeoff velocity. Okay. Now I'm going to clear some space here to do the last part of my problem. So I'll need to do a little bit more algebra. Okay, so that first part of the problem, that delta t, is covering the amount of time where my feet are in contact with the ground here and producing some non-zero force in the vertical direction. Okay, and the net force there, that force minus my gravity in that downward direction, is on average during that time a force of about 214 newtons. It's not always 214 newtons, but on average while my feet are in contact with the ground, it was a net force of 214 newtons. Then my feet leave the ground, and I'm no longer contacting the ground and no longer able to produce any force between my feet and the ground because they're not touching the ground, and gravity is the only force acting on me. Okay? Once I'm airborne there, that's a special case of mechanics called projectile motion, where there's then a special set of equations, knowing that gravity is the only force acting on me, that I can use to figure out the kinematics of my motion, generally speaking. So that's where this second equation that it tells you about here in hint 2 comes from. And again, don't worry if you're not aware of why does it look like this exactly, where did that come from. That'll come up a little bit later in class. We haven't covered those mechanics yet. Here we're just getting some practice in doing these things. So here I want to solve for the value of y2, which is my peak height that I reach after I've left the ground. So if you want to attach some physical meaning to the symbols in this projectile motion equation here, we can do that. And let's draw it out here. So that equation, my pen, was v2 squared minus v1 squared equals 2g times y2 minus y1. Okay, I think this might have been v2 plus v1 actually. No, minus v1. Right. Okay. So let's attach some physical meaning to these things. V1, we already calculated that in the previous step of the problem. That was my takeoff velocity. That's my 2.57 meters per second. Okay. V2 here, that's my vertical velocity when I get to the peak height of my jump. Why? Because what I want to calculate here is y2, which is the peak height of my jump. So V2 here, vertical velocity at the peak of the jump, y2, vertical height at the peak of the jump. So the subscript 2 there indicates the end of my movement, or the end of the movement that I'm considering here, which is the peak height of my jump. The subscript 1 indicates the start of the movement that I'm considering here, which is the takeoff point of the jump, the point when my feet first leave the ground. So here we're going from when we leave the ground until the peak height of the jump, similar to the previous problem where we were going from when we were standing still until when we left the ground. Now we're continuing that further from when we leave the ground up until the peak height of the jump. Okay. So V2, vertical velocity at the peak, V1, takeoff velocity, G is still gravity, Y2, height at the peak, Y1, height at takeoff. Okay. We know G, we were given that. We know the height at takeoff, we were given that. That was the point 2.95 meters, I believe. We know V2, kinda. We got to reason it out here. And we know V1. We already calculated that. That was the 2.57. Okay. So it looks like I can solve this equation. Remember, every equation that you have, every algebraic equation, you can solve for one unknown thing. And I've got my unknown height here, y2. So I can rearrange things here and get y2 by itself. Divide both sides by 2g. And then add y1 to both sides. And you get y2 by itself. Okay. But if you're looking down your list of things you know here, you might say, I'm missing something, right? I've got y1, that's 0.95. I've got g, it's 9.81, negative 981. I've got v1, it's 2.571. I don't have v2. What's v2? Well, we know v2. We got to reason it out from the mechanics. Okay. How do we do that? Let's go back to my example with my Wookiee here. Okay. He's jumping. He leaves the ground. And then he's going up, and he gets up to his peak height. And then he turns back down and starts falling back. Okay. So when he gets up to his peak height, at that instant in time, like if he's jumping, and if you think about freezing him, snapping your fingers and freezing him as he's at the peak height, at that instant in time when he's at the peak, what instantaneously is his vertical velocity? It's our favorite number in math and physics, except for when it comes to grades. We don't like this number, but we like it when we're solving problems because it generally makes things easy to solve. When he's at the peak height, his vertical velocity is instantaneously 0. Okay? The way that I like to think about that is you leave the ground, and you've got a certain amount of vertical velocity when you initially leave the ground there. And that's actually the fastest vertically moving part of a movement like a jumping here. You have your greatest vertical velocity at that point in time. Okay? Then you leave the ground, and then gravity is acting on you in the negative downward direction. Okay? So gravity, we tend to think of it as, oh, what's gravity? Oh, it's negative 9.81 meters per second squared. What does that mean? Think of gravity as being negative 9.81 meters per second, or every second gravity is taking away 9.81 meters per second of your vertical velocity. Okay. So he leaves the ground and he's got some fairly large vertical velocity, and then gravity is going to be taking away that vertical velocity gradually over time as it accelerates him downward or speeds him up in the downward direction. Okay. So what happens when you leave the ground and then you get to the peak height of your jump, and then you turn around and start falling back to the ground, that turnaround point is where you've been airborne long enough for gravity to take away all of your vertical velocity, and it's instantaneously 0 velocity, and then it starts accelerating you downward into the ground, you get a negative velocity. Okay? So even though it's not explicitly told to me in the problem, the key word here where it says, you know, his peak height, what's the peak height that he gets to, that peak height there is your indication that your value here of V2 is actually 0 because he's at the peak height there. So we know V2, it's 0. We don't even need V2. It's got a value of 0. So if I want to solve for my peak height here, it is negative 1 times takeoff velocity squared divided by 2 times gravity plus my takeoff height, which gives me a peak height of 1.29 meters there. Okay. Now, here's one thing where you have an advantage in biomechanics versus in just like general physics in terms of kind of checking your answers here. Okay, so what's a good vertical jump? You know, you might have heard like a 40-inch vertical jump. If you hear about these things in like the NBA draft or the NFL combine, you know, 40-inch vertical jump. That's a pretty darn good jump. And what is that exactly? What's 40 inches of what? It's generally the height of the feet above the ground, or the change in height of any particular part of the body relative to the height when you left the ground. Okay? So we can kind of give ourselves a reality check here. on saying, is this a plausible value that we calculate here, like 1.28 meters in terms of the height of my center of mass above the ground? Is that realistic? Well, let's check it by taking that peak height and subtracting the takeoff height, the height that we started at, which tells me my change in height here that I experienced, the change in height from takeoff until the peak height was about 0.34 meters. Okay, and let's convert that into centimeters, about 34 centimeters, and then let's convert that to inches, 2.205 inches. Okay, so this person did a jump here of about 15 inches. Okay, so is that good? No, I wouldn't say that's particularly good. This was actually some data measured on me when jumping. I'm not the greatest athlete in the world, if that isn't obvious. But is that a realistic value for a jump? Is that a plausible value? Yeah, somebody could reach a peak height of 15 inches above the ground in a realistic human jump. If you had gotten 150 inches here, or 0.15 inches, or 15 million inches, that would probably cause us to kind of raise our eyebrows and think, something's wrong here. I either did a wrong calculation, or Dr. Miller mistakenly gave me a spurious number, or there's some sort of mistake here. Okay? That's one advantage you have in this class versus like a physics class, where you can almost always look at the answers that you get and just kind of through your intuition and experience with human movement and experience in kinesiology, kind of reason out, is this a plausible thing? Like, is it realistic that somebody could jump 15 inches off the ground? Yeah, it's realistic. Is it realistic somebody could jump 15,000 inches off the ground? No, not on planet Earth. So some mistake must have been made there. Compared to like a general physics problem where you might calculate like the energy of the nebulous mass is 1,779.8 joules, like, is that plausible? Well, I don't really know. I'm not real sure. I don't have anything that I can ground that knowledge in. But here in biomechanics, you almost always have some reference through your experience and intuition that you can kind of give yourselves a reality check here. So doing things like that is generally a pretty good thing to do in cases where you can calculate an answer and then give it kind of a check based on your intuition and experience. Is this a plausible answer? Okay, last but not least, let's change our significant digits here. We dealt with velocity, and let's make that 1. Yeah, let's leave it 2. 2 is fine here. And we dealt with height, and let's also leave that with 2. And there we go.